Hello all, welcome to the webinar series of IEEE Joint Chapter of MTT-APEMC CAS Islamabad. I'm Noshirwan Shoaib, I'm the chair of this chapter. I'm also working as Associate Professor at Research Institute for Microwave and Millimeter Wave Studies, also known as RIMMS, at National University of Sciences and Technology, Islamabad, Pakistan. So we are located in Islamabad. Islamabad is the capital of Pakistan. It is one of the beautiful capital among the capitals of the world as well. It has both natural beauty and the business hub, and it is a place where we will conduct our first dedicated IEEE International Conference on Microwave Antenna Circuits ICMAC 2021 in Pakistan. So this will be a first of its kind in Pakistan, and I hope to host all of you in Pakistan in 2021. So keep visiting our website for more details. So as I say earlier, I belong to National University of Sciences and Technology, NUST. It has several campuses in the country, and this is the bird eye view of the Islamabad campus, very well managed campus, and the RIMS, our institute, is located here. So this RIMS is a specialized postgraduate institute that offers degrees in master and PhD in electrical engineering with a particular focus on RF and microwave. We have state-of-the-art research facilities, including anechoic chamber that works up to 40 gigahertz for antenna characterization. We have electromagnetic compatibility and electromagnetic interference lab that is used for electromagnetic classes and also for the compliance testing as well. We have microwave research and antenna lab and also a PCB fabrication lab under one roof. So idea of to provide this facility under one roof is to give the student an hands-on experience so that they can use that experience to get good jobs and good PhD opportunities afterwards. So today we are very pleased to host distinguished Professor Karu from University of Sydney, Australia. He is also the distinguished professor of IEEE APS Society, very well-known professor. The name of the event is many names and many advantages are resonant cavity antennas, the killer planar space-saving approach to get 15 to 25 dBi gain. Brief words about Professor Karu. He's a distinguished professor in electromagnetic and antenna engineering at University of Technology, Sydney, and a visiting professor at Macquarie University, Sydney. According to a special report on research published by the Australian National Newspaper in 2019, he is a national research leader in Australia in microelectronics, in engineering discipline, as well as electromagnetism field in the discipline of physics and mathematics. Professor Karu received BSc degree in electronic and telecommunication engineering with first class honor from the University of Moratawa, Sri Lanka, and master's and PhD degree with near perfect GPA in electrical engineering from University of Ottawa, Canada. Professor Karu has authored approximately 600 research publications and his paper have been cited over 10,000 times. In 2019, his publication received 1,200 citations. He is the first Australian antenna researcher ever to reach Google Scholar H index of 30, and his citation indexes have been among the top Australian antenna researcher for a long time. At present, his I10 is 180 and H index is 49. He is an associate editor of IEEE Transactions on Antenna Propagation, IEEE Antennas and Propagation Magazine, and IEEE Access. He is a track editor of IEEE APS 2020 Montreal Technical Program Committee, co-chair of ISAP 2015, APMC 2011, TENCON 2013, and the publicity chair of ICEA IEEE 8BWC 2016, IWAT 2014, and AMC 2000. He is a very known professor in our community, and without any further delay, I request Professor Karu to please proceed ahead and start his presentation. Over to you, Professor Karu. Thank you.
Thank you very much, Mr. Chair. I think I should start sharing again, right? Let me check. Screen 2. Is it coming well?
Yeah, you may proceed ahead. Thank you.
Okay, great. Thank you very much, Mr. Chair. Good afternoon, ladies and gentlemen. Can you hear me well?
Yeah, I can hear you.
Yeah. Okay. So this is IEEE Antennas and Propagation Society Distinguished Lecture. It's a little bit odd because I am actually the chair of the IEEE Antennas and Propagation Society Distinguished Lecturer Program, But as a past distinguished lecturer, I'm allowed to give lectures. This year, I did not give that many lectures. I was mostly doing selecting and appointing new distinguished lecturers and approving other distinguished lecturers. I have been doing that for 3 years now. Finally, I got this opportunity to give a distinguished lecture to you, to Islamabad chapter. I have been to Islamabad, that was quite a while ago. And unfortunately, this time I had to do it from one of my bedrooms. I'm sorry about that. Nevertheless, I hope you will enjoy it. So you heard a lot about me. I am from University of Technology, Sydney, UTS. And this is my email address, the short one, karu@ieee.org. And this one is one of our fancy buildings, just opened. You can see the UTS sign here that is on top of the tower, a taller tower. And I think you like, the other thing you probably like in this slide is not my photo, but the background of my photo. Can you guess what it is? I think you can guess. It's an antenna chamber. It's an anechoic chamber in my university. That's the largest one, I believe, in Australia and New Zealand. Just brand new. It's just about to be commissioned. So this year I became one of the 2 finalists for Australian National Eureka Prize for Outstanding Mentor of Young Researchers. And they've honored a video and photos, and you can see my video in YouTube. Just Google my name and you will find that, or UTS. And this is, so I chose the background to be the anechoic chamber. It's really beautiful, even when it is out of focus. So we have really good facilities in this university. As you know, I was with Macquarie University for a long time, for 26 years or so, and moved to UTS last year. So before we get to the presentation, let me check whether how to go to the next slide. Okay, so that is Sydney. You can see some icons here: the Opera House, the Harbour Bridge, and this is the city of Sydney. Cruise terminal, the big Hyde Park, and my university is right here. That's our tower, which is in the middle of city, bustling city. But now we have our labs, some of our labs a bit away from the central CBD in Botany area near the airport. Usually at this point, I explain a little bit about IEEE Antennas and Propagation Society, but because you had already distinguished lectures from APS this year, I will go straight to a little bit about my university. And these are some of the buildings. You can see some strange looking buildings, and this is my building. Not this side, but it's a relatively young university. As you can see, became a university in '88. It's a technology university, but it's pretty large, about 45,000 students, 30,000 undergraduates, 10,000 postgraduates. Large. And the other real interesting thing about UTS is its quality. Its international ranking, in world ranking, it has been going up quite well. This one is 2020, actually 2021. After that, it was There was another one that it came to like 120, I believe. In Australia, it's ranked number 1.
Hello, Professor. I think your voice has been disconnected. Can you hear me?
वो स्लाइड भी रुकी हुई है रैंकिंग वाली स्लाइड
यहाँ पे जी वही रैंकिंग पे प्रोफेसर करू कैन यू हियर मी
आपके साइड से तो नहीं इशू
नहीं सर उनकी साइड से ही है
अच्छा चलिए
he left and then I joined them in again thank you
अच्छा तो उनसे कि कैमरा भी ऑन कर लेंगे अगर पॉसिबल हो
सर वो कहते हैं वो जो स्क्रीन वो यूज कर रहे dear participants, we have a brief delay in the connection. We resume in few minutes. Thank you for your patience.
Hello.
Yes, Professor, I can hear you. I think there's a disconnection. Can you please share your screen again? Thank you.
Can you see my screen?
Not yet.
How is it now?
Okay, no problem. You can because I can't see the share screen here.
Okay, I will reshare it.
Okay, no problem. Thank you. Yes, it's online.
Yeah. Good. So I think somehow internet connection dropped out somewhere.
Yeah, no problem. Please continue. Thank you very much.
Okay, so where did I say this? So it's, in Australia, it's ranked number 1 among young universities under 50. And globally, it's ranked around 10th or 13th among the young universities that are 50 years old or less. So then a little bit about my group. I think most of you know a lot about my group. Center for Collaboration in Electromagnetic and Antenna Engineering. We focus on high quality research. A lot of our PhD theses are ranked in top 5% or 10% of the world, 52 of them. We have a lot of, we publish a lot in IEEE, Transactions or other journals. We have a lot of publications, you already learned that. And all our quality of work is reflected in these other things, impact, etc. But these are just side products. What we try to achieve is good quality research, that's all. All these other things, awards, a lot of awards for me and my students, they are byproducts of our research. As I said, we are very well funded by industry and other organizations, governments, and you can find information in my UTS website or my Macquarie University website. Let's go. We collaborate a lot with universities and other organizations, companies around the world, a lot with universities in Europe. I think because we are running out of time, we will go fast, and these are some of my students. Quite a few of them are from Pakistan. You may know some of them. Then let's get to the business. Okay, about the material. So I have a lot of topics. I don't think I will be able to cover all of these, but if I can get somewhere close to near field phase transformation, it will be great. So I will go fast track. Okay, what time you want me to finish for questions? Maybe a few minutes before, right?
Yeah,
so let's get to the resonant cavity antennas. So these, one thing you want to be very careful about is these antennas have a lot of different names. No other antenna has so many names. Electromagnetic Band Gap Resonator Antennas, so EBG resonator antennas. Resonant cavity antennas is the one we normally use. Fabry-Perot resonator antennas, so Fabry-Perot cavity resonator antennas. Partial reflector surface, so PRS antennas, and even called 2D leaky-wave antennas. But basically, they are more or less the same. Actually, they are exactly the same in terms of operating frequency. They have some sort of a ground plane or fully reflecting surface. They have a partially reflecting superstructure, and there's a resonant cavity in between them. Normally, this resonant cavity is filled with air because air is free and lossless. That's quite good, but you can fill it with anything else if you want. And the cavity is excited using a feed antenna. That's pretty much it. It's very simple configuration. It has the advantage of being planar or quasi-planar. I already said simple configuration. You can get high gain without a large feed network. Very high overall efficiency. Have very high aperture efficiency. You can get any polarization you want, LP, circular polarization, CP, or even dual polarization. Some of the really interesting features are they have extremely high directivity bandwidth product per unit area. I will show that a little bit later. The only limitation I can think about is they are a little bit bigger than microstrip patch arrays and slot arrays. But you get a lot out of this. This concept was described by Trentini long time ago, even before IEEE. At that time, it's IRE, Transactions on Antennas and Propagation, in 1956. He called this a partially reflecting sheet array, the one in the top, and it calls reflex cavity antenna because it has reflections, it has a cavity. It's very similar to the way even now we describe the antenna. But then they evolved a lot. So I said about the superstructure. You can use many different types of superstructures in these antennas. In this case, the superstructure is a one-dimensional dielectric stacks. Few stacks of dielectrics, no metal. In this case, the superstructure is this printed two-dimensional periodic printed structure like FSS, frequency selective surface. In this case, the superstructure is actually a piece of a 3D EBG structure, like a wood pile. So you can design it anyway in a lot of different ways. And these are some of our prototypes. You can see this is dielectric slabs. These are also dielectric. These pieces are all dielectric. That is the air cavity. and this is the ground plane, and that's dielectric, air cavity, and ground plane fed by a waveguide, and these are some 2D printed superstrates. The part I want to cover today are kind of recent history from about 2006 to about 2016-17, that period. And after that, there's a massive expansion and there are a lot of papers. So I can't possibly cover it in this lecture. But this period has been very interesting. I will explain why. When Alex Ferradisis of UK published this paper in 2006 with this antenna with the PRS with a gain of 20 dBi and bandwidth of 10%, it was a world record, that bandwidth. But in about 10 years, we got antennas with about the same measured gain, 20, and with measured bandwidths of about 50 to 57%. So you can believe, you can see how much change, and they all have different type of superstructures. Some of them are from my group, some of them are from other groups. All of them got good gain, which I mean greater than 15 dBi. Actually, only this one has less than 15 dBi. So you can see this revolution or progress in this period of about 10-11 years. So why we were interested in this? Because we have been working on all these periodic structures for other purposes. Artificial magnetic conductors, photonic crystals, EBG structures, extremely wideband reflectors for ultra-wideband applications. This is also like artificial magnetic conductor, but extremely wideband. Other frequency selective surfaces, absorb and transmit frequency selective surfaces for wireless communications. They are all periodic structures. And there's a lot of theories, tools to handle periodic structures. So we applied that in this area. Very early days, Dr. Andrew Wiley, one of my postdocs, designed this photonic crystal 3D wood pile and measured its characteristics, and he made a lot of nice things out of it. Took a rod, one of these dielectric rods, made it a defect waveguide, coupled, matched it with metal waveguides, and measured transmission. It's the same thing, same data. In dB scale, you can see the penetration of the field into the EBG structure and the decay. And then he designed couplers, bends to bend electromagnetic waves by 90 degrees by removing again some dielectric rods. So the input, we remove this and we remove the other one in the lower layer. And he can design this such a way that this bend, the 90-degree bend, does not reflect wave. Rather, the wave jumps down to the lower level and comes out here. Very interesting things, but these are early days. And also we designed some horn type antennas without metal. Only the feed is a waveguide. Everything else is dielectric. And we published these things in IEEE Transactions. So these are the early days, like 2006. You can see the interesting field penetration and confinement in the photonic crystal. Then our collaborators in Spain, in Pamplona, extended this idea. We published jointly other type of horn arrays, evanescently fed horn arrays. That is 6 years later in 2012. And this is one of our original resonant cavity antennas based on that wood pile. So took a piece of wood pile, left a gap, air cavity, ground plane, ground plane, and then we need to feed this air cavity. We did it using a double slot feed and a waveguide underneath. Quite simple, and we got some very interesting results. These were again 15 years ago, the early days of these antennas, and it's still interesting to see how the wave in the waveguide couples to the cavity and penetrates through the partially reflecting 3D wood pile structure and radiates into air. So what happens after? Then we try to find ways of making this simple. The 2D periodic structures are much easier to fabricate than those 3D wood piles. And they are also very thin, so you can make very low profile antennas using 2D printed FSS type superstructures. They are just like superstrates. So that's one of our early designs, 2012 transactions. We got 13% bandwidth with a gain of 16.7 dBi measured. That was a huge, big deal those days. Then we also tried those what we call resonant cavity antennas inspired by 1D periodic structures. So this is not really a 1D periodic structure, it's only 3 dielectric slabs. But it's if you extend it becomes a 1D periodic structure. So our first designs are fairly simple but very large. And later we figured out that by truncating, making them quite small, you can get much wider bandwidth without compromising gain. So all our later designs were like this, quite small. But still it has the same features, a ground plane. This is the air cavity. And then this is the dielectric superstructure. In this case, the superstructure has few dielectric slabs and air gap as well. And it's fed by a linearly polarized microstrip patch here. The cavity is fed by a dual band LP. So this is a dual band antenna. Dual band linearly polarized antenna. This is also a linear polarized dual band antenna with the stack patch feed. That was also published in IEEE transactions. We opened it up, you can put it down and then form the resonant cavity here. This is a circularly polarized dual band antenna. It's very easy to convert linearly polarized one to a circularly polarized one. All you have to do is to change your feed antenna, this little antenna. If you can see here, you can see 2 truncated patches, right? And these 2 are for the 2 bands. It has 2 separate ports for the 2 bands, and each generates CP in its own band. Okay, then a lot of other designs published in transactions and other places. All these are dielectric. The superstructure is full dielectric. Sometimes it has a air gap as well, but that is a composite dielectric superstrate and then the air gap ground plane. And they are all very small. You can see 2 lambda naught by 2 lambda naught is the superstrate area, 1.5 by 1.5 lambda naught in this one. They are very small. And then when you look at these, they have different superstrates. You can't probably see that. Some of them are 2 layers of different dielectrics. So there is a variation in dielectric constant in these antennas in the axial direction. In the superstrate. In this case, I think there are 4 different dielectrics in the superstrate. One of them is air. So we call this RCAs with axial permittivity variation. Okay, but there's no other variation sideways or transverse. Then in this paper, we explained that antennas with transverse permittivity gradient have much better performance than those with axial permittivity gradient. In this case, we have only one slab, but we change the permittivity, highest permittivity in the middle, and then we decrease the permittivity. And the rest, we have a air cavity and a ground plane fed by the slot and a waveguide. And in fact, the ground plane can be as small as the superstructure itself. So now we have two methods to design this. One, the superstructure could be something like this, dielectrics with axial permittivity variation, or it could be something like this with transverse permittivity gradient. And it turned out that after doing a lot of research, this one on the right is a lot better in terms of performance. The only advantage of the axial one is it's easy to fabricate. So you can see those side by side. These all have axial permittivity variation. This published in Transactions AP in 2014 and Electronics Letters in 2016. The ground plane can be larger, little larger than the superstructure, or in this case, the ground plane is the same area of the superstructure. This is the air cavity, but we filled it with foam, and from here to here is the superstructure. And this is our first prototype with transverse permittivity gradient, and it's here. That's the air cavity. This is the ground plane, slot, and a feed waveguide. It is quite small, and as you can see, we needed only 3 different dielectrics to realize this. Although in theory you can use many, you can get good performance with only 3 dielectrics. So these are some of the results from those papers and transactions, etc. I will skip some of these. This is one of the interesting results. This is the superstructure area. So we are changing the superstructure area, and you can see the peak directivity. In the special antennas, the directivity, you can make the superstructure small, but the directivity does not decrease until you make it really, really small. The green curve is 3 dB bandwidth. See what happens to that. When you make it small, the bandwidth increases. Is on this scale. So in this area is really good. You get this almost the same directivity and gain and much bigger, much larger bandwidth from a very small antenna, which is easy to fabricate and small and fit in small places. But if you try to do it too much, then you end up with high side lobes somewhere here. And if you make it even too small, then you lose directivity. So there's some really interesting operating area somewhere here. And that let's skip some of these. Some theoretical papers. These have been published in. We looked at changing the thickness of these superstructures. These are few different thickness values. We increase the thickness by 25%. You can see that you can get a better bandwidth by changing the thickness without compromising the directivity. You lose only 1 dB directivity, less than 1 dB, and you get a lot more bandwidth. That's one option you have. So this is our first prototype with 54% gain bandwidth, measured antenna with a gain of measured gain greater than 15 dB. Okay, I will probably not go through the design methods because this is available in a lot of different papers. Because we are running out of time, there are a couple of methods. Optimization, we tried various methods, genetic algorithm, particle sum, cross entropy to optimize these. This is one of the genetic algorithm application. I think we done this with our colleagues in UK and published in AWPL. In this case, the printed pattern, it has printed patterns on both sides on this single superstrate, and that pattern was generated by genetic algorithm. So this is the unit cell for the lower surface. This is the unit cell for the upper surface. Yeah, this is our AW paper with Professor Yang Hao, Queen Mary, UK, etc. Then we used a lot particle swarm optimization, PSO. I'm not going to go through the PSO basics. I'm sure you're familiar with this. The interesting thing we did was, in early days, the optimizers in commercial design systems like CST Micro Studio, they are not very advanced. So we wrote our own optimization code in MATLAB. CST did the simulation, and these were coupled automatically. So CST does a simulation, send the results to MATLAB. Our MATLAB optimizer analyzed that and change the parameters, create a new model, and then send it to CST. So this happens automatically, iteratively, until we get a good result. And we did optimize quite a few antennas like this. Again, skip some of the details. Let's get to one of those. So sometimes you run it a few times and you get several solutions, but they are not that different at the end. These three are almost the same, and the other three are almost the same. Then we fabricated and measured and published some of them, right? Now, this is one of the really good products. My authors, Dr. Afan Baba is working in industry now in a company, and Dr. Rahil Hashmi is an academic. Both of them are from Pakistan, by the way. This is really good one because it was challenging to optimize this. We want to get good bandwidth, increase the bandwidth, and also increase the gain. And so we had to increase the size a little bit to 2.6 lambda naught. And we had to change the thickness of these dielectric segments in the superstructure. I don't know whether you can see it well. They have different thickness values, and we had to use 4 different dielectrics in this case instead of 3. But we got really good results, 57 gain bandwidth, and we managed to get a peak gain greater than 20 dBi. And we measured it, and these are computed results. It got better side lobe levels than the one that is totally flat. And these are the measurement results in our 2017 paper. So peak gain compared with a couple of our other papers, one a recent one, the one I showed you, and the other one a bit older one, also from my group. We got much better gain than that. This one did not have the bandwidth. This one had the bandwidth, and this one new one got even better bandwidth. So gain bandwidth product much higher than those previous designs. Gain bandwidth product per unit area. Actually, this one we published in 2016 in Transitions, got the highest gain bandwidth product per unit area, 1,300. It dropped here because we made it a little bit larger. So to summarize this, and also to compare these with lens antennas, because some people confuse these with lens antennas. These are not lens antennas. These are totally different to lens antennas, because we have a resonant, we have a cavity here, multiple reflections between the superstructure and the ground plane. In a resonant antenna, in a lens antenna, it's basically one pass. You try to avoid reflections from the lens, but here we need reflections from the superstructure. So they have totally different characteristics. The advantages of the resonant cavity antennas are here. They are very small area-wise. New designs 2 to 5 lambda naught squared. Thin, around 1 or so wavelength, and directivity bandwidth product per unit area or gain bandwidth product per unit area is extremely high. So you get a lot of gain and bandwidth from a small area using these antennas. On the other hand, they cannot replace lenses in all applications because lenses can give you much higher directivity if you want. Of course, they are taller and bigger height and area, but it gives you higher gain, higher directivity, and in some cases much larger bandwidth as well. But you pay by the height and the size. So they are complementary technologies for different applications, not competing technologies. Now in the next few minutes, I will just wrap up this method called near field phase transformation we developed. The history behind that is, as I said before, you can make really simple resonant cavity antennas like this. Just a ground plane, a very simple patch or some other feed antenna, air cavity, and one or few slabs, dielectric slabs. And some cases you need only one slab, and it works for simple projects like undergraduate projects. So this is with the one slab. You can see it still works. It's matched, easy to fabricate, but it has a problem. The problem is its phase is not uniform in the aperture. Because of that, you don't get the best directivity or gain you should get from that aperture. So for that, we need to do phase correction. But the way we did this is in the near field. So we call it near field phase correction or near field phase transformation in general. First, we have done by designing something like this. It's a bulk dielectric phase correction structure. It's in transactions in 2015. That worked, but it's pretty bulky. And then we've shown that we can change this profile in a paper in 2000 in Journal of Applied Physics. But this is probably the most interesting for engineers. Basically, these are all lenses. Okay, that is true. This is like a lens. It corrects a phase. So we converted this bulk full dielectric thing into a flat panel phase correction structure, which is printed. It's multi-layer printed structure with patches, several layers of patches printed on PCBs. And that's in transactions in 2016. So this is the bulky one, as I said before. The directivity without the phase correction structure is this, and with the phase correction structure it is here. So you can see the gain in directivity, increase in directivity, and also the gain by about 9 dB. And this is the flat panel one, the printed phase correction structure PCS on the same antenna. That's quite thing. The whole antenna system is less than 1 lambda naught. Again, we got about 9 dB increase in directivity. Okay. So just to check how it works, these two animations can explain. This is just the RCA, resonant cavity antenna, with a very simple phase, partial reflecting structure, just a one slab. You can see that the near field phase is not uniform. And this is the same antenna with the phase correction structure, the planar printed phase correction structure. You can see the near field is very uniform phase. And that's the reason why we get high gain, high directivity, and high aperture efficiency from this antenna system. Okay, so that is fun, but we did more than just phase correction using this near field phase transformation method. We actually managed to steer the beam of the antenna. In this case, we use a planar high gain antenna, of course, in this case, resonant cavity antenna as the source or the base antenna. Then we created two metasurfaces, metasurface 1 and metasurface 2. They are specially designed phase transformation metasurfaces, and they are placed in the near field, very close to the antenna, very close to the RCA. And then we rotate these metasurfaces around this common axis to steer the beam. So we don't do anything to the RCA. RCA is fixed. We only rotate these things. We don't tilt anything. So the whole system is quite thin because there's no tilting. You can see this method in our paper in Transactions in 2017, and several other groups extended this method for several other applications. You can see you can find who has referred to them. Some developed theoretical methods. Professor Yaya Ramaswamy's group in University of California, Los Angeles in USA came up with the phase method to predict the beam direction, and there are a lot of other work in Europe and other places in China on this method, beam steering method. So how does this method works? It's based on the so-called optical Rayleigh prism. Imagine this is an optical laser beam, and the first metasurface behaves like a prism, or a dielectric wedge, or an optical wedge, or a prism, and the second one is another prism. So if you have a laser beam and ignore the top one, just apply it to a prism, and you rotate the prism, the laser beam will go like this, like its direction will change on the surface of the cone. If you put another optical prism above it, then actually you can tilt the beam even more, the laser beam up to somewhere here, and also you can fill the middle. You can actually direct it to any direction within this large 3D cone, three-dimensional cone, to any direction by rotating this. So let me show this in an animation. This one is easy to understand. What we are doing here is we rotate, we keep the RCA, the base antenna, fixed. In fact, you can use any base antenna, not just an RCA, any base antenna, fixed antenna with a fixed beam. You don't need to steer, and we steer using these metasurfaces. So we rotate both metasurfaces in the same direction. When you do that, the beam direction, the azimuth angle of the beam direction changes, as you can see in the top figure. The elevation angle does not change. In the lower one, we rotate the two metasurfaces in opposite directions. Can you see the red lines moving in opposite direction? Now, the azimuth angle of the beam is the same, but the elevation angle changes. And you can go even the other way if you want, this way, that way. So plus or minus 50 degrees or so. So we prototype this. These are our metasurfaces. Because I am running out of time, I will skip these details to the last graph. To the measured pattern. You can see by changing the beam direction, you can change rotating the metasurface, you can change the beam direction. In this case, both sides along theta equals 0, and here theta is something like 50 4550. And the drop in gain is only 3 dB. With less than 3 dB gain variation, the beam of this antenna, which is 19 dBi antenna, can be turned to any direction within a large cone with an apex angle of 102 degrees. That is plus or minus 51 degrees. So those are the results you can find in our paper. And the method has a lot of advantages. Totally passive. It doesn't need any active components. It needs only power to rotate those metasurfaces. That can be done by a couple of low power stepper motors, for example. Can handle high RF power if you want. Very high efficiency because there are no losses, no active devices, no phase shifters, etc. And it does not need any tilting, so it's planar, low profile, and quite less expensive to fabricate. So that is where I think I should stop, because it's all 5 minutes to 7 in my time, in Sydney time, 7 p.m. Mr. Chair, I think I should stop here and let answer questions if there's any.
There are a few questions, but I think you can take maybe 5 more minutes to conclude the presentation. Then we go towards questions. Thank you.
Okay. It's very hot here. Actually, I'm sitting now. Let me have a little bit of water. I have a lot more slides, so they actually I would not worry too much in those. But about maybe about this beam steering. What I meant totally passive is it does not need any active electronics. Metasurfaces are passive, the antenna is passive. So only part that needs power are the motors to rotate the metasurfaces. It can handle high RF power. Actually, there's a paper published by a Chinese group. After we published this, they designed an antenna and metasurfaces using metal only for a high power microwave system. You can see that it's in IEEE transactions. Very high efficiency because these metasurfaces are nearly lossless. The antenna has very low losses. The overall RF efficiency of the whole system is usually 80%, 90% in that range, depending on the dielectric you use, but not like when you use phase shifters, etc. Or large distribution networks in phased arrays. The loss in the distribution network is quite a lot, especially at higher frequencies like 20 gigahertz, 30 gigahertz. Because we don't have active components, there's no active nonlinearity or active intermodulation like IM3 products. There's no thermal dissipation in the antenna at all because of the high efficiency. So there are no thermal management issues that are common in thin electronic beam steering systems. And low cost is because the way you can fabricate these things. Planar, no tilting, I already said. The other antennas like reflector dish antennas, mechanical or mechanically tilted to steer the beam. There are horn arrays and other types of arrays. You probably know those are used in a lot of defense systems and aeroplanes to get Wi-Fi from satellite to the airplane. There's one you can see hump on the top of the airplane. That is a flat panel. That is the antenna, and some of them needs tilting. Some of them needs tilting to steer the beam, and that is why they are taller. So in this case, lack of tilting is a major advantage to keep it very low profile. And it can be concealed in a box. Because there's no tilting, it's just a flat box of certain area and certain height. You can design it with any type of base antenna, as I said before. Some other groups have done it with various different type of base antennas you can find in the literature. Some CTS, continuous transfer stub type antennas, and the group in China I mentioned, the high power RF power group, used a horn antenna as the base antenna. Basically, any base antenna with a fixed beam can be used. And my students and in our other projects, we are using many different types of base antennas depending on the application. Okay, we have few projects going now in this area. They are all different applications. Some of them for wideband applications. So because the antenna is totally stationary, you don't need RF joints, and because there's no tilting, you don't need expensive motors. That's why I think I should stop here. I think we are getting a little bit of network problems again, right?
Yes, I think we can start the question and answer session.
Sure.
Okay. Thank you very much, Professor Karu, for your very interesting talk. There are a few questions in the queue. I asked one by one. So the first question is regarding the superstrate. So you have shown a number of superstrate that are using above the antenna. So is it possible to use an active superstrate like using diodes or to have this beam steering application?
Yes, of course. You can use active superstrates, or you can use active ground plane, or you can use active both. The important thing is changing the reflection coefficient. You can use active methods to change the reflection coefficient. I did not go through the method of designing, right? The reflection coefficient of the superstructure and the reflection coefficient of the ground plane are important. If you use just a metal ground plane, it is fixed. It's like 180 degrees, right? But you can use other type of fully reflecting ground planes like artificial magnetic conductors or a reconfigurable ground plane. People have used that actually. Reconfigurable ground plane with active devices. It's easier to use active components on the ground plane than in the superstrate because those devices need bias lines, and the bias lines can interfere with your wave. Unless you find some smart way of making it really thin and not interfering, there could be some complications. If it is a linearly polarized antenna, you can run the bias lines orthogonal to the polarization with less effect. But it's a lot easier to use active components in the ground plane and run the bias lines through the ground plane without affecting the field. Okay.
Yeah, thank you very much for the answer. There are many questions now. So one question is about the commercialization of these RCAs antennas. So the question is the industry or how to commercialize these RCA antennas, or if they are, what is the transition from academic publications to commercial usage?
We are working with some specific organizations, but I wouldn't call it commercialization. It's, as far as I know, there is no commercial product that contains an RCA. but I had few slides where it's basically in areas where I think I can explain in areas where this could be used in short range point-to-point communication systems, for example. If you need this level of gain, 15-20 dBi or dBc circular polarization, wireless link, and with the kind of wide bandwidth, right? Bandwidth can be changed between 10% to 50% or even 60%. And this is a good method to achieve that. So there's some hope that in 5G type applications, millimeter wave 5G feed networks, for example, to feed micro cells, so small cells, wirelessly without fiber. For example, if you want to set up a 5G millimeter wave station in somewhere very quickly, then you can set it up and then you can feed it with this kind of antennas wirelessly. It's a backhaul, right? Wireless backhaul, millimeter wireless backhaul. And now with the beam steering, it can be very, very useful because you don't have to tilt the antenna. You can steer the beam using those metasurfaces. So I think those are potential applications in the near future in the telecom area.
Yes, very true. I think the next question is a bit linked because the question is, can the beam stream antennas be used for 5G base stations? If yes, how do they provide the enough resolution?
And I don't think that is. It may be possible, but not exact the way it is in this, in the way I presented, because okay, now some 5G base stations, the traditional base stations have fan beams, but as you have seen in papers, now they are looking into pencil beams for 5G. But very fast switching between beams. Because this is mechanical, beam switching time is not very not like microseconds or like that. So I don't think, unless you try to do it with active devices, as you said, the mechanical rotation will work. But some other people are working on. There are other ways that may be useful in base station antennas, but not in the classical sense, like a fan beam, 30-degree beam or 120-degree beam.
Right. I think the next question is about the fabrication of how do you fabricate the transverse changing permittivity material? So maybe it's regarding the challenges.
Yeah.
Yeah.
Well, we did it in the easiest way. Just they were designed to use commercially available material, and then we just asked the workshop to cut it to the right shape and just press them together. That's all. And I mean, we were a little bit worried that there could be some little air gaps that can cause problems, but they did not cause any problems. So it's very, very robust, tolerant method of fabrication. But now the fabrication world is changing, as you know. There are a lot of other ways of printing, high quality 3D printing. Dielectrics are emerging. Actually, we use one high quality 3D printable dielectric, but for one of the metasurfaces. But we did not actually print it with their material. We asked them to machine it, but it can be printed. So with the availability of more range of materials that are low loss at high RF frequencies, that are 3D printable, I think that issue will be less and less problematic.
Yes, you're very right. So I think we conclude the session now because we have reached the time, and I'm very thankful to audience as well for their questions. If you have any further question, as Professor Karu has already mentioned his email in the start of the presentation, so you may also contact Professor Karu. Now I would like to thank Professor Karu. Thank you very much for your very interesting talk, and it was our pleasure to host you. And hope to meet you again in Pakistan, maybe next year, when we will conduct the first dedicated RF microwave conference in Pakistan.
Yeah, thank you very much for organizing, and I really thank you all for attending, and hope you found this interesting.
Thank you very much, Professor Karu. Have a nice day. Bye-bye.
Bye-bye.